And so I guess I actually started my career in college doing computer vision, studying robotics and bioinformatics. And then my first gig out of school was building, FPGAs that went into orbit for Lockheed Martin that would do atmosphere and compensation. And we do, all the way from bit and cycle accurate modeling all the way through Verilog code. Ended up spending 5 years at Penn State, basically implementing a really rudimentary version of Keras before it invented. It was before it was actually invented. And so got a lot of experience messing around with modeling at that time. Then I decided to take that and go work at Planet Labs, where I've actually met Rose. And that was kind of a place where I got to see really, where remote sensing could happen at an enormous scale, right? To see how these pipelines were put together so that you could do, daily global revisits across hundreds of satellites and constellations, right? And that was pretty eye-opening because I got to work with some pretty interesting folks, like the Frank Mormadans and Kelsey Jordals of the world, to see kind of like where the old school pipeline world meets the new school kind of deep learning world, right? After that, I went on to Orbital Insight. And Orbital Insight had a much bigger emphasis on machine learning as a service in that paradigm, right? So it was a nice place to see, how companies might split up the training data set creation, the machine learning components, and the ultimate deployment of machine learning as a service models, right? Also, it's kind of nice because it was a nice playground where you could play around a lot with like synthetic data generation, semantic segmentation, object detection, these kinds of things. Then finally, about a month ago, I made the jump to Maxar. And there, in the last month, it's been really quite interesting to see, the projects that they're working on. And I'm really excited about the future of remote sensing as a result. I think, they're really starting to try to think about the revisit problems and the cadence problems that we might see often in remote sensing, and trying to create the future hardware that's going to produce these very, very, very large scale data sets, right? There, so far, I've been allowed to work on like swap problems, size, weight, and power, and latency constraints for machine learning applications. So that's been really cool. And also focusing on trying to reduce the data set sizes so that analysts can actually make use of these massive data sets, right? So that's me.
Awesome, thank you, Manny. Next up, we have Dalton Lunga.
Hi, thanks, Rose. I'm equally excited to be part of the discussion. So I work as a senior research scientist in geospatial image analytics at Oak Ridge National Laboratory. So as part of the team, I develop and deploy machine learning and computer vision within HPC environments. And the goal there is to derive large-scale data sets whereby we are mapping features from remote sensing images at country scale. And these data sets are finding their way in impacting multiple solutions. For example, we are supporting population distribution estimates. These are being done, as I mentioned, like at country scale. We are also supporting efforts to, assess damages in the wake of disasters. These being done as well, like at multiple country scale. When an event like, drops on Earth, then we are required to process large troves of imagery. So my current research interest has sort of like moved into two areas that we have sort of like discovered over the course of 4 years, that these tend to be recurring in most of the applications that I work on. So the two techniques that I've been focusing on are, one, domain adaptation, the need for coming up with machine learning that can generalize, without the need for retraining models. I found it to reappear over and over again. And the way that we're doing it in a different method is to, take back into some of my background in, during my PhD, where I focused on manifold learning. So we're looking at manifold-driven, models that looks at pairing data as well as trained models, so that the reuse of models that are already trained is increased, and the matching of where models would work is also done within the manifold geometry. I'm also looking at incorporating UQ uncertainty quantification methods, so as to help and guide, and calibrating some of the models that we are working with. So one thing that we've discovered, over time is that when it comes to extrapolation, machine learning fails dismally. The models don't know what they don't know. So we are hoping that through UQ, we can help to, guide how models can learn to estimate what they don't know and present what they don't know to the human, so as to augment, that gap to provide estimates that are reasonable, or things that can then feed into decision-making without being exposed to a lot of vulnerabilities. And yeah, I'm looking forward to this discussion.
Great, thank you so much, Dalton. Next up, we have Jake Shermeyer.
All right, hey all, excited to be here. My name is Jake Shermeyer. I am a research scientist at a group called CosmiQ Works. If you're not familiar with CosmiQ Works, we're an applied research lab. I sit at that intersection of computer vision, deep learning techniques, and the geospatial domain. So there's a lot of different stuff we are interested in, mainly around computer vision, as I said. One of our main projects that you may have heard of is called SpaceNet. So SpaceNet is a nonprofit LLC, and it's a partnership with multiple organizations, and it's both a data set and a challenge series. So the data set is really ultra high resolution or really any resolution remote sensing data from a number of different companies. So Maxar, SAR data from Capella Space, Planet Labs data. And the reason this exists is to open source some of this data, make it available for public consumption, and also provide machine learning labels to try to drive some research in this domain. Some of the other outputs from SpaceNet is really our open software. So we open source the winning solutions from our challenges. And also we do a lot of evaluation and applied research studies that we write about in our blog and in academic papers. In terms of my personal experience with deep learning, so I've done a lot of work in terms of benchmarking, object detection, and segmentation approaches, overhead data. I've just led a large research study on the value of synthetic data and created an open source data set called Rare Planes. So here we're investigating the value of synthetic data from that overhead perspective. Specifically, can we use gaming engines to generate synthetic satellite imagery and labels, and how does that help potentially improve your performance when working with deep learning approaches and geospatial data. Finally, one of my last interests is synthetic aperture radar. So investigating really the value of very high resolution synthetic aperture radar and how that intersects with deep learning techniques and how we can get the most out of these new data sets that are starting to become more and more prevalent. So again, really excited to be here. Thanks for having me, and I'll turn it over back to Rose.
Awesome, thank you, Jake. And then last up, we have Sherrie Wang.
Hi, everyone. I'm Sherrie. I guess I'm a 6th year student at Stanford now. I'm getting my PhD in applied math at the Institute for Computational and Mathematical Engineering. I'm advised by Professor David Lobel in Earth System Science, and our group works on studying how food security, food production interacts with the environment. And through that work, for the last few years, I've mostly been working on mapping crop types around the world. And this is especially difficult in places in the world where we don't have a lot of ground data. So we've been working to test a lot of methods out in the US, but then ideally we want to apply them in sub-Saharan Africa, South Asia. And so we run into difficulties of not having that much ground truth. So to work around that, or to find innovative ways to deal with that issue, we try things like unsupervised learning, unsupervised representation learning, using crowdsourced data, and then more recently transfer learning with the focus on meta learning. So some of that work is going to be, my collaborators and I have some of that work at IGARS actually. So hopefully we'll get some good feedback there. And what else? I'm also part of the Stanford's Sustainability and AI Lab. So it's a joint lab group between a professor, so my advisor, a professor in economics, and a computer science professor. And I think it's one of those really cool interdisciplinary collaborations in an academic setting where you bring expertise in machine learning and domain expertise together to work on projects. So there we've done things like using satellite imagery and nightlights to map poverty, mapping where brick kilns and concentrated animal feeding operations are, and things like that. So that's my background. And yeah, thanks for having me.
Awesome. Thank you so much to all the panelists. We're really excited to have you here today. Thanks for your time and your participation. So with that, we're gonna hop into some questions. This first one, we're gonna concentrate on this setting the stage, what makes us different. So let's introduce the remote sensing domain in the context of machine learning or of deep learning and computer vision. So panelists, if you feel inclined to answer a question, just go right ahead. If you don't have anything to add, that's not necessary for each question. So we'll just see how that goes. But for first question, what would you say are the main differences, both advantages and disadvantages, of remote sensing compared to the general computer vision or deep learning space?
All right, I'll kick it off if no one else wants to. So I think one of the main things that makes us different is really just this interplay with the Earth. So we think about a lot of different settings here. You know, the effects of sunlight, for example, seasonality, weather conditions, all of these things can really affect the types of collects you're trying to get from space, and really cause unique challenges that you just don't face in traditional computer vision. On top of that, you know, just varying geographies. So, you know, stuff that is, you know, for example, a house in the United States is certainly not going to look like a house in Southeast Asia or Sub-Saharan Africa. So you really have a lot of heterogeneous features that can be challenging and tricky really to model quite well with computer vision or deep learning. You know, beyond that, I think a lot of the features are typically smaller, and we typically have less resolution to work with. So when you have computer vision models, typically they're trained on really large photographs where our features are thousands of pixels in size. Sometimes we might only have tens to hundreds of pixels really to identify features. So that's another challenge. So these are all disadvantages, but I don't know. I would also say that it's kind of an advantage because it makes it fun and a diverse field. And also means that a lot of the approaches really are not always one size fits all, and would work. So I'll leave it there and turn it over to another panelist.
I'd say to add to that, you know, in terms of the challenges, right? You know, the odd revisit rates and the odd periodicities that we deal with. You know, if you're trying to figure out some sort of pattern of life, and you get, you know, your first image comes on Tuesday at 11 in the morning, your next image is too cloudy to process, and the image after that is a month later and it's at 5 p.m. You know, it's really hard to establish, you know, the stationarity of the statistics you're trying to model, right? And so I think those go in to make this problem particularly difficult. Then of course you have like platform issues where, you know, your platform might be running hot, and so that kind of changes the physics of the sensor that's pulling down the data. You might have a gimbal that's messed up, so you know your pointing accuracy of your model is not quite right, and so therefore you're trying to figure out, you know, how orthorectified am I really, and all these kinds of questions. Those are all neat, right? Those are all cons, I would say. On the other hand, it's beautiful. I mean, every day you get to look at imagery that is just gorgeous, which is definitely on the pro side. Another pro would be, you know, the imagery for the most part is somewhat far field compared to other domains, right? So everything is kind of far away and flattish, with the exception of like slant angles and very, very tall objects and things like that, of course. But that sort of kind of limits the difficulty of the problem to some degree. There's other companies that are still kind of taking those slant angles and reprojecting into 3D domains to like really maximize their accuracy for orthorectification, things like that. But it's still kind of ultimately like a far field problem. And I think finally, the feature space is really well matched to like convolutional neural networks, right? The imagery that's coming in, you know, things are sort of spatially correlated in a very local domain. Whereas if you go to something like NLP, you know, you're really worried about like maybe embeddings and abstract syntax trees and a high degree of abstraction that make that problem particularly ill-posed or challenging. And a lot of that goes away in the EO kind of like sensor data domain. It'll come back, of course, when you start integrating like other sorts of sensor modalities and things like that. But it's kind of a fun place to start and play with and see some good results pretty quickly, right?
I would also like to add that, oh, sorry.
Sorry, go ahead, you can.
Okay, thank you. I would also like to add that there is another dimension for 3D models and for 3D deep learning, for reconstruction of like urban spaces, etc. I mean, in traditional reconstruction, you can have that, let's say, sphere that you can sample views from for object reconstruction or for whatever you are reconstructing, like actor reconstruction, etc. But for geospatial reconstruction and for urban reconstruction, it's actually a little bit more, I don't know whether it's a disadvantage or advantage, you can like claim both sides, but what is there as a fact is that you have like 2.5D that you are trying to reconstruct, and that's actually somehow organizing and like providing you an implicit understanding for the model, so that you are actually just laying a sheet on top of the earth, so that your reconstruction is actually as like surface, not smooth, probably not convex, etc. But it's a surface that you can fit to, and that actually makes the 3D reconstruction problems with convolutional neural networks or with deep learning a little bit more well-defined and more understandable for the model itself.
Yeah, I was just going to add to what has already been said, that so one of the basic notions that I see the differences between everyday computer vision and remote sensing problems is if we look at the data itself. For example, I mean, with most data sets in computer vision, there is this mimicking aspect of processing or modeling on what a human can see, whereas with remote sensing imagery, what we are mimicking is like a bird's eye view. So we have a lot of context that surrounds the object that we're looking for. But with that, one of the challenges that I see as more problematic for us, as already mentioned by Jack, is the fact that when you have the high revisit rate and also the change in view angle, the labels that we are creating, they're giving us a single snapshot in time. And when things vary, we are still looking at using the same labels from one snapshot over different, angle variations, and that is a problem.
Yeah, I agree with everything that's been said so far, and I think related to some of that is that more on an image level, there's obviously in natural imagery, there's mostly RGB imagery, and in remote sensing, we have RGB imagery, but we also, often have 4-band imagery with near infrared, and then there's shortwave infrared and vapor bands, and then we have SAR, and there's just lots of different bands that you could be working with. And so I think that's both an advantage and a disadvantage. So it's good because we have more signal, like we have more information that we can analyze to solve whatever application problem we're looking at. But at the same time, that means that, like, if I had a natural image problem, I could just take a pre-trained neural network that was trained on ImageNet and then apply it, fine-tune it on my data set, and then I would expect that pre-training to really help with my natural image problem. But in remote sensing, because ImageNet is an RGB, but a lot of our applications are multispectral, we found in the past that it takes a lot of finagling to adapt those models, and there's a lot of work to show how that can be done. Or you just want to train from scratch or train on some other remote sensing data set, because the ImageNet weights don't actually even contain the features that help with the task that we care about. So yeah, I think that's one challenge, and I think that's related to developing canonical data sets in the remote sensing domain, and then delivering along with those data sets the pre-trained weights that could help someone with their application. But another challenge related to that is the fact that whereas I haven't really heard people complain about analyzing natural images from different digital cameras or different cell phones, but you obviously run into complications if you're trying to use a model that was trained on Landsat imagery at 30-meter resolution and then apply that to planet imagery at 3-meter resolution. That's just totally different. So there's just more different sensors, and then that means we need like a whole model library potentially to help people get a head start on their training.
Great, thank you all so much. If you're new to this domain of remote sensing, you can see that it's definitely very challenging and very different from these conventional domains. So maybe just pushing a little bit more on these challenges, would you say that there's any specific types of models or types of data sources, types of satellite sources that have been particularly challenging? Or going from the other side, have there any that have really been more revolutionary and very successful with helping you answer these questions?
I'll just hop in on this one. I think what I've noticed since I've worked at a broad set of companies, some companies that don't produce imagery at all and just ingest many different types of imagery, right? My feeling was that there's not really a silver bullet for a data source type, right? Everything has its pros and cons, you know, like if you're looking at, let's say Dove imagery, you know, you've got 3 to 4 meter resolution and you do get daily revisits, but 3 to 4 meters is pretty rough to do, you know, object detection and these kinds of things, right? If you're looking at, you know, Maxar data, it's really, really high resolution, but we're still working on making that, you know, have the same cadence that you might require to do, you know, the sort of pattern of life studies that you might want to do. If you're looking at SAR data from NDA or ISI or Capella, you know, it's great in that it obviates the cloud problem, but you know, any little motion in the object and you're going to get all sorts of ringing of energy all across the image, and that has its own challenges, right? And then, you know, you look at kind of like the medium resolution stuff like Airbus and SkySat coming in at like 0.7, 1.2 meters. That's pretty good for those larger objects. But I think from some of the studies we've seen out of CosmiQ Works, kind of the Nyquist rate for some of these smaller objects is around 0.5 meter or higher resolution, right? So I think the interesting part about that domain is that it allows a lot of people to ingest all sorts of different types of information and try to understand how they can create better fusion-based estimators from all those different sources, right? And it's pretty hard to find data sets that have good co-locations, but you know, I think that there are some resources out there and that allow you kind of to do those studies, and then that might in the future push the types of sensor platforms we might put in the air, right? So
I would say the data set depends on the task that you are trying to explore. I mean, if there are so many things that we can learn from the Earth, right? And finding the right data set for the right task is the key. If your motivation is just to like get your hands dirty with computer vision and deep learning, then that's like, there are some, I don't want to say toy, but there are some simple data sets that are starting with RGB, like CNNs can like train in a reasonable time if you are lacking compute resources, etc. So maybe like first training your model, or first like understanding what each layer in an architecture is doing in that easier data sets is something that would make you even more excited for the field. So because you will see that, oh, like whatever whatever information was in the imagery, this model actually has an implicit knowledge about that object or type or label or whatever you are training for. Then go through like, then you will see that there are so many tasks you can do with deep learning on satellite imagery or on like multiband imagery. And then you can like focus on one that like, okay, I will find all the water sources in this area because I want to deploy an automatic like water detection system in this area. Then you go for like from image quality or like from image format to the spatial format, which country, where, what is the data source, etc. So I would say first get your hands dirty. When you are and expert, or like you don't even need to be expert, but when you have an internal understanding about what is the differences of the satellite imagery, what is the differences in models, in deep learning models, what is the receptive field, how can I change that? When you are comfortable with that, find the task. What is your impact? Why are you doing that? If it's for, it can be for the sake of research, of course, but find that particular task, then find a data set that is suitable for that task. That's my 2 cents.
Yeah, I can add on to that. So what we found to be successful in our workflows has been, I mean, from the initial phase when we started to, do large scale mapping where we were processing, we are processing large volumes of data, would be to say you could leverage, open source labels data, even though they are very noisy. However, to deliver a product that is usable, to your stakeholders or your sponsors, what we then found to be very good at getting a product that is usable is the fact of leveraging the transferability of models that are trained from open source data that is noisy. However, when we have a task that is very specific, we will then fine tune our models on clean sample data sets that are created just to be tailored for that application. So the transferability, still leverages the broadness of the model that you would have trained, from otherwise, noisy labels, but you still have enough knowledge to make that model more generalizable while still fitting on that specific, task that you're looking at.
Yeah, if I could expand on that a little bit, Dalton, I think like what we found, it's very similar, right? So at some point, whether you're using like, a single pass or a 2-pass object detector, YOLOv 3, 4, 5, whatever, what have you, most of your improvements comes from your ability to fundamentally understand the features of the data set that you're training against and how that maps against your target environment, right? Which to me says that a big amount of the investment should go towards creating very robust, informative feature sets and representations of the data so that we can engineer our data sets to train in the right way to produce the best performing detectors, right? Or the best performing model, right?
I would also add, I agree with everything that's been said about choosing the data source that matches your problem and how transfer learning can be really helpful in our field. So for what we do in agriculture, it's really the temporal signal that gives us a lot of information about what's growing on the ground and how good is the yield of the farmer and stuff like that. One thing that hasn't been mentioned is I think the label source. So I think Dalton mentioned this in the first question, that a lot of like natural image tasks can be done by humans. So there are things that we intuitively understand how to label, but things in remotely sensed imagery, a lot of that takes some sort of expertise in order to label. So if you're asking someone to label, what is a smoke plume or what is a crop field, like you do need to teach them those labelers and do some training before they can really recognize exactly what you're looking for. So that makes getting very large numbers of labels really difficult. So, so related to your question about what kind of data sources have been successful or challenging, I think in real applications that we've dealt with, we've tried crowdsourcing, and that's been both successful in some senses and very challenging in some senses. So successful because crowdsourcing allows you to get this vast volume of data that you otherwise, if you sent surveyors into the field to do, either delineating crop fields or telling you what crop type is growing there, or it could be something, in the forest where you survey what tree species and stuff like that. That takes obviously a ton of man hours, and it costs a lot too. So crowdsourcing is really successful in gathering a very huge amount of data. But at the same time, it's super noisy because you have people who are untrained. You have people who kind of just submit samples for fun, or maybe they're sometimes trying to game the system if you are paying them to do it. So there's a lot of challenges to making those sorts of data sets usable. But I think that's a really promising avenue to explore because labels are so scarce in our domain.
Awesome. Oh, Jake, did you want to add anything?
Yeah, I'll be quick, but I mean, just to tie it up here, I think everybody made a lot of really good points, but you know, just in terms of having data that's available for research, that can be a real challenge, particularly when you have very high resolution sensors. You know, there's tons of great data sets out there in that Landsat Sentinel domain. You know, the raw cost of data can be quite limiting. You know, that's really why we tried to start SpaceNet and get data sets out there where we have some of that open source data. It may not be the feature types you're interested in. We do building footprints and roads right now, but I think, again, that could be a great place to start, learn something, and then have a model that might be transferable to another domain if you do some pre-training on the SpaceNet side.
Absolutely. So we're going to transition now, talking a little bit more. We've now been introduced to a lot of the challenges. So solutions, how do we scale these things? How do we deploy them? So question here is, the world looks totally different from one country, even from one city to the next. But many of you are working at these large country scale, regional scales or larger, and having success at deploying these models at these large scales. So what's your approach to scaling these models successfully across geographic regions? For example, do you find that you might need to train models dependent on specific regions, or alternatively, do you have ways to create more widely applicable and generalizable models?
I can jump in here first. So I would say again, initially when we started, you know, with this effort, the approach has been, and I've seen this repeating in some aspects in different applications, whereby it's a trial and error approach. You train a model, it fails because the distributions are different between the training data and where you're testing. And then you look for the samples, you know, within your test domain. Maybe it's few samples that you can quickly label. You add that to the original training, you improve the model, then it does better. You move on. So that is kind of like, I mean, the initial matching approach, where we like, you know, depending on the need, we would train for one country, deliver the product for one country, move on to the next country. We do the same thing, where we end up with our analysts having to, you know, label, you know, new samples so that we can have models that fit and do the learning better and do the feature extraction so that the data products that we're putting out are usable. However, after receiving, I mean, you know, a huge number of countries, we started asking the question that, I mean, you know, how long are we going to, you know, persist with this marching one country at a time? Because now if we have to do 5 countries all in one go, that means we have to either, you know, double or 3 times or even 10 times the number of analysts that are helping in terms of, you know, creating the labels that we need for our supervised learning models. So from that question, we then started to look back in terms of, I mean, you know, the data itself without being constrained by the geography. So you can think of an approach whereby, I mean, you know, if I told you that you needed to map the features being map all the buildings for 5 countries or map all the roads for 5 countries, then the question for me as somebody who's doing machine learning is, okay, how can I come up with a model or a set of models that can work across the data set for all the 5 countries? So that prompted us to then look at rather approaching this from understanding the underlying geometry of data and hence manifold learning, whereby with all the data, we would sample using some criteria across the data that covers, say, 5 countries. So 5 is just a rough number. It could be 20 countries. Then from that representative sampling that we're doing, we create an underlying geometry upon which we can then fold back all the entire imagery of the 5 countries to the manifold space. And then in that manifold space, we create different models for regions in the manifold space, not necessarily informed by geography, but so after looking at the metadata as well as the contents of the imagery. And we've seen this approach inform better reusability of models, because models that we train for a few, selected imagery that is covering like 3 countries can be reused in different geographies. So the notion of reusing the model then avoids this geographic constraint, but you're dealing with the data in the manifold space.
Yeah, I would add that the problem of creating models that generalize across space and time is generally just really hard, and deep learning models are pretty notorious for being quite brittle, so that if you trained if you trained a CNN to classify cats and dogs, but all the images are maybe of the cats and dogs outside, if you then had pictures of them indoors or in a different setting, there's no guarantee that that classifier would actually be able to do well in that setting. So I guess what we're doing right now is we're looking into meta learning methods, which is one very rapidly developing subfield of machine learning and deep learning. And there have been some algorithmic advances in the last three-ish years where you're able to view a bunch of different data sets as different tasks. And you train a model not just to do well on each task, but to learn how to do well on a new task. So if we look at the remote sensing domain, or if we look at data from all over the world, the way that we could frame that in a meta learning, under a meta learning framework would be to view different regions in the world as different tasks. And you're trying to find models that can adapt well to a new region given very little training data in a particular region. So that work, I would say, is still very nascent, but I think looking into the latest in the field of deep learning on transfer learning, meta learning, continual learning, I think that will help us solve some of these problems. But even in computer vision with natural images, I know it's still a big challenge.
Yeah, that's some really good points there, Sherrie. I think some of our work has also shown that really the complexity of the task that you're interested in can really affect how well your models can transfer to new locations. So for example, we did a test where you train a model just to detect all the aircraft in an image. That can transfer pretty well to new locations because it's a simple task. It's a one class task, right? But as you up that complexity, say you want to detect or separate out where all the fighters are versus where all the transports are, or then maybe you want to go a step further and detect the actual make or model of an aircraft, the generalizability really starts to decline the harder the task becomes. So I would say, maybe starting simpler is certainly a good approach as well. And also, I think maybe just if you can have some historical observations and train on those locations first, I think that can also help boost your performance in your areas of interest in the future.
I would also add that I agree with all of these, and most of those tasks most of the approaches that we talked about are still depending on some data to begin with. They are like supervised approaches, but I definitely see that since the scale and distribution of geospatial data is actually kind of more uniform than like any images in the wild, right? So then you can actually apply more semi-supervised approaches like human in the loop approaches, so that you can actually add more quality to your data while you are also learning, like continual learning kind of. And that I have some hope that semi-supervised or weakly supervised approaches for remote sensing, for deep learning or remote sensing imagery also show some promise that those transferability tasks, like even evaluating whether a task is a task is suitable for being transferred for one geographic location to the other geographic location itself is a research topic itself, whether maybe that task is not transferable, or maybe you need some, again, like human in the loop process to actually apply some of that transferability or some of the labels or some of the transition, or even if you are looking at 3D, maybe you need some data augmentation process to morph the data of one location that to look similar to the other location, so that your deep learning network can also like be transferred from that data to the other data. Anyway, so I think that going a little bit further from very nicely quality labeled data to more noisy labels and or weak labels, or even like unsupervised approaches, is also another key to apply generalizable deep learning networks, deep learning methods for different locations on Earth.
So this all makes sense to me too. I just wanted to add a little bit of an intuition to something Jake said, which is, you can probably train a reasonable aircraft detector that works in like 1/8 of a hemisphere using efficient DET and something like that, and like, less than 15 megabytes in terms of the size of the model, right? And so it stands to reason that the underlying thing you're learning is relatively simple. It's just a matter of exposing it to the right amounts of data. And the approaches that I've seen that work best, that globally generalize, is really about painstakingly selecting your data set to make sure that you have good coverage across all the variants of the global space that you're looking at, right? Again, I hate to beat a drum, but I think that comes back to like really fundamentally understanding good representations of your data set to make sure you cover the variants well.
One quick question from the audience. What about transfer over time? So say from year to year, as opposed to one country to another. Any insights there?
I actually was about to jump in and make that comment that I think we've all given the generalization aspect in space, geography. However, things can vary in time. On the same point that you're looking at, I think Jake made the comment at the beginning that, with the sign elevation, and also I think from the SpaceNet 4 dataset, that is a good example where things can vary in time and still you run into big issues in terms of trying to generalize a model that works on one set of collection to another set of collection. So that is a big challenge that we are also facing. I'm interested to hear what others think of that, and I'm glad it's a question that's coming also from the audience.
I have one comment on that, which was, when I was working at Planet, we had daily revisits, right? And we would create these mosaics every month. And doing that generalization, even month to month, was really quite challenging. And part of that was, of course, because the sensors had different degradation properties and things like that over time, but also because the satellite folks were changing gamma curves and things like that on the platform to fundamentally change the distribution of the statistics on you, right? So you had to pay really close attention to like which flock was going up, possibly how long that flock was around, how well the registration happened from one flock to the next. It's very much a challenging problem, and I think it really speaks to what I think is one of the big challenges in this space, which is land use change detection and being able to do that effectively over varying different types of scales and different types of geographic locations, right?
Yeah, this is a perfect opportunity for me to pitch SpaceNet 7, which is launching September 8th. So it has 100 AOIs of planet data, so 24 monthly mosaics typically for each of those AOIs. So this is really going to be focused on urban change detection. So not only are we extracting change, we're also tracking each unique building over time and seeing if it appears or disappears. Not to mention you have to account for things like clouds appearing suddenly. Or unusable data, like Manny was just saying, where you've got some distortions in the data that might not render it particularly usable. So yeah, we're excited about that. We're excited to see how it turns out. We actually developed a custom metric just for this. So we can track, we're not only tracking the buildings, we're also calculating the amount of change. So I think we're excited to see how deep learning and this data set really intersect, and hopefully it provides some good insights in this space.
So Jake, so on the SpaceNet survey, not to say that you should, or maybe expand more, how are you handling the labels? Are the labels varying over time as well? For that data?
Sure, yeah, so for each monthly mosaic, each one of those was annotated individually, and they actually used a higher resolution base map to do the annotation. So we have, it's interesting, you actually have labels that are a higher resolution than the planet data in a sense here. So that's going to be another interesting test where we might have some coarser imagery, but we have these really high quality labels. Can you still work with this coarser planet imagery and be able to still pull out these buildings?
Great. So we're running a little bit low on time. I want to try to get to 2 more questions, one more around these solutions and then one more with sort of closing remarks. So in terms of this next solution question is more around scalable solutions. So we have this amazingly diverse panel from industry, from academia, from government. What are your insights into the actual deployment of these deep learning and remote sensing problems? Again, you're working at these multi-country scales. So what would you say is the best approach to convert from more of a research prototype into a large scale self-sustainable solution? And also enabling this potential for very large impact from those solutions.
I think an easy answer, and it might not be sexy, but like kind of the intense quantification and baselining of what you're actually going to deploy. A lot of our research is focused on like what resolution is good enough. Like, is 30 centimeter appropriate for this challenge? Can you go to a meter? Can you go coarser? Other aspects like how much data do we need? All these are really important for understanding before you really just try to deploy something. Your inference speed, how fast it needs to work. And finally, kind of something like data standards. So if you're trying to deploy something globally, do you want to go with commercial data that you're going to have to constantly have that dollar cost assigned to it? Or can you work with something in the open domain like a Sentinel or a Landsat? And perhaps that might actually be the more appropriate choice, especially when you're doing something maybe like land use, land cover change detection over time. That might be a global application.
Yeah, I have to agree. Oh, go ahead.
Yeah, I can add 1 or 2 points that I think the approach that we've taken is to sort of like, we view the training of the models as one component of, a training, of an entire workflow. There are other pieces that are crucial to deploying the models. The aspect of having to deal with, the pre-processing of data matters a lot, because if your pre-processing pipeline deviates between deployment and training, then the models would perform dismally when you deploy them. So having to design a workflow that, incorporates both of these at the beginning can help, to sort of like, remove some of these pitfalls. So the other thing, as already mentioned, is the aspect of the deep learning acceleration of the inference itself. That matters depending on the volume of data that looking at processing. So we've had to move from each component from, pre-processing, the training, and then accelerating the inference itself. But because we are sort of like pushing out data layers that are being used for decision-making, we don't stop at the inference. We also have a QA/QC component that helps to address some of the false positives and the errors that we see in our models, so that we can have the human jump in on the QA/QC component and catch some of the errors. And if we are able to then retrain the models to reapply them at large scale, we can do so with that, closing the loop. I think Ilke mentioned the need for having a human in the loop. That's where we see the human in the loop playing a huge role for deployment workflows.
Yeah, I think I will generalize that. And for different, again, for different tasks, where there are different definitions even for deployment. So maybe for the research community, even the release of dataset and easy access and download and playing with tools for datasets is actually a deployment of not the model itself, but the dataset itself. Then there is a second level that you maybe train a model on a dataset and have some accuracy on that specific dataset, but you actually open source your data, your deep learning model, and then that deep learning model can actually be deployed in other places, other tasks, other locations, other datasets, and that's a way of releasing your deep learning model. And then there is the last layer that you are actually creating an infrastructure around this ecosystem of deep learning models that it can work for most of the data set. The data set is bounded. It's not being run or being trained or being like run inference on a data set that was not out of the distribution that you initially trained with. And that infrastructure is actually very important for deploying those models, because the end user doesn't know much about your deep learning model, but the quality of the data they are mostly concerned on. So that puts more emphasis and more importance on your deep learning model to be more generalized and always have similar accuracy, like predictable predictions on most of the data sets that it may be posed with, etc. So the last layer of deployment there, you need to think about many things, like can it cover everywhere, not everywhere, but everywhere within the definition, within the requirements of the model. Can it pose any unwanted consequences for any type of labels or people or geographies or locations or villages, etc.? Or can the deployment of this model be create some unwanted friction between the use of the model and the deployment of the model, etc.? So those, like, from the beginning and to the end of the deployment, there are many other aspects that you need to think about when you are deploying deep learning models. And I actually want to shout out for my team in Facebook and MIT about having some pilot successful deployments about a very useful, very impactful project in India, where we actually use a generative scheme. So I want to talk just a couple of sentences about that. So there are deep learning approaches that we talk about right now, which are based on analysis approaches, right? Like object detection, segmentation, recognition, etc. Then there is the synthesis approaches, where there are GANs and variation autoencoders, etc. Those are creating new samples, new observations from the data that you already have. And this project that I just mentioned is actually a generative model where we are creating street addresses for the billions of people that live without a street address. And that, when you look at it at first, is that creating names, creating some social constructs, like addresses are like humans create addresses. Addresses doesn't occur in nature. It's just like maybe hills and something, but like even roads and streets are constructs. So creating something that is well defined, mostly for humans, in a generative setting is something that you need to be even more aware of the consequences at the deployment. So I just wanted to say that, like, for analysis approaches, you are providing some values from analysis, but for synthesis approaches, it's even harder to create those to create paths for deployment for something that is created based on data, not just observations. So yeah.
Cool. I just have one thing to say, I would say, related to this, since I've seen it done a few times at different places. I think what you're going to see is if you're joining a new company and you know you're going out there for the first time, you're going to see that over the last 5 years, because the tools have come along a long way, you'll see companies that previously had implemented their own deployment systems, right? They'll have their own DAG to manage, you know, how they scale up their instances and how they do their storage and all that kind of stuff. And a lot of them are quite married to those infrastructure. And so it's you know, they might be using, you know, a lot of home rolled code that still uses like Kubernetes and stuff like that, right? But I think that the tricky part is to make sure that you find that healthy balance between having legacy infrastructure that your company developed and not being afraid to roll out these new libraries that have a lot broader open source support, so you don't get like boxed into like a very specific set of capabilities, right? And so, you know, companies might be using, you know, companies now might be afraid to try something like MLflow or Kubeflow because they've created their own DAGs. You know, and so it's just like really important to like strike that balance. I think as scientists and engineers, we really like to say, oh, we're going to build this ourselves, right? We'll build every little aspect ourselves. But it's really important to leverage what's already out there because there's a lot of really great, well-supported work out there. So I'd be worried about that a lot, I think.
Great. So we have about 10 minutes left. I just want to give everyone an opportunity to give sort of closing remarks or more looking forward remarks. So I'm going to ask 2 questions, and then panelists, you can choose which ones you want to answer within about 2 minutes. So the 2 questions are, 1, first, do you have any advice for people that are looking to get involved in this domain of remote sensing and deep learning? And going along with that, any specific recommendations for resources or tools to get started with? And then the second possible question to answer is, what would you say are some of the biggest opportunities for the advancements in this domain over the next couple of years, or like the lowest hanging fruits and opportunities for people to get involved in? So we can go in the same order that we started, if that's okay. Ilke, if you want to go first.
Yes, I can. What was the first question? Sorry.
First question is any advice or recommendations of tools for people that are looking to get involved?
Yes, I was actually just writing that in the chat that like anyone wants to start with a simple enough data set that's still with a simple enough data set that can run some challenges on road extraction, land cover classification, and building detection. Deep globe challenge is still there. It's not a challenge anymore. It's just a data set and benchmarks related to deep globe, but you can still go to Codalab and submit your results and see where you are related to the people that are submitting their challenges throughout the earth. And I can say that there are over 100 solutions, and even the papers that are based on deep globe are approaching to 200. So you can benchmark your new models on this data on many people, against many people. For advice for newcomers or advice for people, start with simple tasks and understand the underlying theory. I mean, you don't need to go like all deep to the each like formulation of each mathematical construct maybe, but know what each layer is doing, know why you are applying that many layers, know which features you are looking for, know what is the difference between the features that appear in ImageNet versus the features that that appear in another data set with the same architecture. So are you seeing the same thing in the layers, or which loss function is good for which problem? What is the properties of your data set? So when you are comfortable with correlating all of these questions to each other and say that, oh, okay, this data has that like class imbalance problem, so I should apply this loss function. When you are as comfortable, then you can like proceed and find a real problem, real research problem, or real like impactful problem that are helping the people on Earth. Then you can like seriously go with all of these like more advanced levels, let's say. So try try starting your skill build with simpler tasks, I would say.
Thank you. Manny, anything from you?
Yeah, absolutely. So I guess what we're going to see in the coming years is an explosion of data, right? And we've sort of seen it in the past, but I think now it's really coming. Particularly in a self-plug, I think the birds that we're going to be putting up in the next year are just going to increase the revisit rates and the resolutions to a scale that we've never seen before. And so that's really going to make it very important to figure out how we can extract those little needles of insight in that ever-growing haystack of data, right? So I think that's going to be a fascinating problem to see develop. It's a problem we didn't quite have yet, but now it's coming, so that's cool. And then as far as advice goes for people, you know, like my favorite saying from my favorite book is fear is the mind killer, you know, from Dune. So don't be afraid to just jump in and dive in and get your hands dirty and play with data, you know, and it's available. You can find it in sources from DeepCore or from OpenSpaceNet. It's all around you. And the nice aspect of this field is that it's so new and so fresh that if you try something that you don't know you shouldn't try, there's a high chance that it could yield something useful, right? So don't be afraid to dive in. The tools are all around you, and go get it.
Awesome. Thank you, Manny. And Dalton?
Yeah, I would say three things on the second question in terms of opportunities to advance, you know, deep learning or machine learning in general. The first one being the opportunity to, you know, come up with models that can work and take advantage of less, you know, data sets. So I would say if investments are pumped into creating active learning methods, domain adaptation methods that relies on fewer labeled samples, we will start to see a growth in terms of the impact and the potential of machine learning in remote sensing. The second point is to do again with the fact that machine learning models are data-driven. So by design, they do not, you know, factor in the physical laws. So there is an opportunity for us to start, you know, incorporating some of the domain awareness knowledge that comes with the fact that we do have things that are represented in space. So geography can play a role in terms of informing, you know, some knowledge that can be incorporated into machine learning. And the reason being that we know that deep learning, machine learning you know, the models are pretty bad at extrapolating things. We can only do so well if your test data is overlapping with your training data. So when you move out of that, you know, training data distribution, you're bound to run into errors. So there is hope that incorporating these geographic constraints could help to stretch the impact of machine learning. The last point that I'll make would be to say that I think if we can start to see a lot of investments that are encouraging cross-domain research in the form of taking advantage of not only remote sensing, but incorporating some of the vast amount of data that is collected on the ground, bridging the two to inform our world has potential to transform the current state of the art that we have in deep learning and remote sensing. Yeah, thank you.
Thank you so much. Jake, would you have anything to share?
Sure. Yeah, in terms of advice or resources, you know, maybe you don't even have to jump into deep learning right away. There is certainly a cost barrier in the sense that you need GPUs typically to run or train these models, but you can learn a heck of a lot just by spinning up a simpler machine learning model on your laptop with a CPU in there, and learn quite a bit. I mean, I cut my teeth on the Landsat data set and spinning up random forest models to detect land use and do mapping like that. So I think that's a great place to start if you want to get into the deep learning space. We have a package called Solaris available on the CosmiQ Works GitHub that kind of abstracts away some of the challenges. So you have to deal with the projections, the geolocations, all the geographic minutia, making it a little bit easier for people to get spun up on that. In terms of looking forward, I would say I think SAR is going to be a really up and coming sensor in the sense that we've got a lot of companies launching really high resolution sensors very soon. Actually, Capella just launched one on Monday. So that means we're going to start seeing really new types of data be available, not only for purchase, but I know they're going to be open sourcing data as well. So understanding how deep learning interacts with high resolution SAR And the interplay between that and existing optical data sets, I think, is going to be very interesting to research and study in the future.
Great, thank you. Yes, so many exciting things are ahead. Sherrie.
Yeah, so I think for the opportunities that I see on the horizon, I agree with Dalton that physics-guided or knowledge-guided machine learning is going to be really important and interesting yet to incorporate all of the domain knowledge that experts already have. I think also lowering the barrier to accessing remote sensing imagery, at least from a computer science perspective, is going to really allow people with deep learning skills already to contribute to this field. And I think tools like Google Earth Engine, which we haven't mentioned yet, but we use a lot in our lab, or like, Rose, Descartes Labs is also making that a lot easier for people. So I think the more we lower the barrier of entry for people with, say, a computer science background to access the imagery that we work with, the more talent there will be to work on problems that are important. I think we already talked about building models that generalize across space and time. That's good. That's super important as well. And I think interpretable deep learning as well, and maybe farther down the line, because this is still really hard, to have some sort of knowledge discovery and not just prediction through machine learning. So for advice and resources, I guess to conclude, I personally learned deep learning in a structured learning environment, like through a lot of coursework. And then the remote sensing side of things, I learned on the job in my lab because there were a lot of very patient postdocs and people who are willing to teach me stuff. So I would say if you can find structured learning resources, I think that would be the first way to go if you have the time for that. So there's Coursera, there's Deep Learning AI from Andrew Ng on the deep learning side. And then on the remote sensing side, I'm sure there's also courses, on Coursera and edX for that as well. And I think for getting started playing with remote sensing data, I think for me, Google Earth Engine was, again, really helpful because it also abstracts away a lot of the things with projections and various corrections that I didn't know anything about when I first started in the field. So you don't have to worry about that. And then you can export data very easily. You can do a lot of analysis on the cloud for free on Google's dime. So you don't have to worry that much about how much capacity your own computer has. And yeah, I think starting out on a platform like that where you don't have to worry about details would be a good place to go.
Great. Well, thank you everyone so much. Thank you to all of our participants. Right before we close up, I'm just going to hand it back over to Nathan, who's going to close it out. But thank you everyone so much for coming. It's been a really great discussion.
Yeah, thank you, Rose. Thank you to all the panelists. I've really enjoyed this discussion. Apologies for not getting to all of the audience questions. We're already discussing how we might follow up with those questions. The panelists don't know this yet, but we're thinking this might take the form of a social media campaign or conversation. So be sure to use the links that I just posted in the chat to join us on Twitter or Facebook or YouTube, so that you can follow up with however we end up following up with the audience questions. So I appreciate everyone submitting and being as engaged as you have. One more call out for IGARS that's coming up soon, as well as some of the webinars that are also this month and through the fall. Specifically, YP Mixer, Young Professionals Mixer. Please join us for that. I'm super excited about it. I'm looking forward to the opportunity to be able to get to know some of the audience members here that I don't know and I haven't had a chance to interact with. In this virtual world where we don't have that chance at IGARS, this is a pretty unique opportunity. So be sure to join in. So with that, we'll close out. And I, again, want to extend the thanks to the panelists and all the audience members, and specifically Rose. I appreciate you moderating this webinar today. So thank you all very much.
Thank you.
Thanks, everyone.
for having us.
Well,
Thank you.